Come on. And it lags. Good. Okay, so lots to do, session 30. So a quick overview. I wanted to highlight some of the important stuff we proved last time, since we had some important results like the mean value theorem. Then I alluded to this in the bird's eye view that we would relate the sign of the derivative to whether a function is increasing or decreasing on an interval. So now we're going to make that rigorous, prove that today. One sort of flavor text way of interpreting these statements about graphs is to think about them as the position graph of a particle which is moving. So this is really the first kind of application to physics, and it's going to remind us of kind of the motivation that Newton had for defining or really describing, really discovering this notion of the derivative, which we spoke about a while back. So we'll do some physics here, and then the second derivative has some heavy proofs to really show that the second derivative tells you concavity, which way a function opens. So we'll just get started with laying the groundwork for those proofs today. Good. Thoughts or questions on the plan?
You know, does is acceleration linear or exponential?
Under what force? Like, for what object do you mean?
Gravity.
What do you say? Wait, I didn't hear. What was the answer? Oh, gravity.
Is
Gravity, yeah. So for gravity, acceleration is a constant, to a good approximation. So if you have an object sitting in the Earth's gravitational field, and it's, I don't know, very small compared to the Earth, so we can approximate the gravitational field as being a constant. So you'll say that there's an acceleration with some constant which you write as lowercase g downwards. So then you would say the acceleration, a of t, is some constant little g. So the acceleration is constant. The velocity, as we'll see later, since acceleration is supposed to be the derivative of velocity, so you can ask the pretty simple question, what sort of function should I write down so that if I take the derivative with respect to t, I get the constant little g? And the answer is pretty clear if you think for a second. I should take t and multiply it by g, since if I take the derivative here, g is a constant, so I power rule the t and get back a g. But there's actually a freedom to add some second constant, which is sometimes written v sub 0, because when I take the derivative of this constant, it will vanish. It's 0. So this is taking the derivative, and then, of course, the velocity is supposed to be the derivative of position, so you could play the same game. And it's pretty easy to guess. What do I have to do so I get this derivative? Well, I want to get a t, so I'm going to need to have something with a t squared and a 1/2, because the power rule is going to bring down a factor of 2. So I need a 1/2 t squared and a g. I need to take the derivative of this v naught, or take the derivative of this product and get a v naught. I need a v naught t. And then I have the freedom to add another constant, because when I differentiate it, it'll go away. So anyway, so that's more than you were asking. You were just asking, is acceleration due to gravity linear? No. Acceleration due to gravity, to a good approximation, is constant, not linear.
okay.
Good question, though. I should emphasize this is only an approximation. There are nonlinearities. I mean, the full Newtonian expression for the gravitational force F, which is really a vector gravitational between two objects, is the mass of one of them, say capital M for the mass of the Earth, times the mass of the second one, maybe it's an object, lowercase m, a constant which is written capital G to distinguish it from lowercase g. So this thing, and then divided by an expression which means the distance between the two particles, so we usually write that as r, and that is squared. So it's this thing, but it's a vector, so you need a unit vector here, which is sometimes written as r hat, or I guess really it's, well, yeah. R hat means it's pointing from the object you're talking about towards the other one, because gravity is attractive. So anyway, this is a recurring theme that we've seen. You have some complicated equation. This depends on the distance between the two objects, and then you say, well, this equation is complicated. In the case I care about, the distance between the two objects, well, the distance between this particle and the center of the Earth is basically constant. I mean, relative to the center of the Earth, it's only moving a little bit. So I can just pretend that r is constant. Then I throw away all of this complicated stuff and say it's approximately constant, so let's just do this. Um, sorry. That's way more than you wanted to hear, so good. Other questions about this stuff?
I have no further questions.
Excellent. Okay, so the rapid review. So this was, I don't think I highlighted this quite enough last time, but I just want to make it very clear that we really got the answer we wanted to for finding maxima and minima last time, but we needed two main results, right? As I emphasized, we really needed the extreme value theorem, which we proved in chapter 2, which guarantees that a function, a continuous function on a closed interval actually hits its max and min. So we needed that guarantee that the max and min are achieved. And then we did this splitting up points into 3 classes last time. And we proved that the max and min have to occur at one of those. So logically, you need both of these. You need to know the max and min are achieved, and then you need to know the types of points at which those max and min occur, and then you can combine them to get the more powerful theorem, which tells you that if f is continuous on the closed interval ab and differentiable on the open interval ab, then it definitely hits both its max and its min. You know they're achieved, so we're guaranteed that they exist. That's the first part we have. Existence is guaranteed. And it gives you kind of what I'll call an algorithm, or a way to find them. It gives you a step-by-step guide to find where those max and min occur. It's very easy. You just find all of the points that satisfy one of these 3 conditions. Either the derivative is 0, or it's at the boundary, or the derivative doesn't exist. And look at the values at all of the points in those 3 groups and pick the biggest and smallest. So I think the existence is more interesting. I mean, we proved that that these are guaranteed, so that was a theoretical exercise. The algorithm is really a cookbook. These are the steps you follow to find the max and min. But I just want to be clear on that. So this is the main result, and a lot of the high school calculus or AP calculus AB and BC problems will just give you some function and some interval and say find the max and min. You have to go through this cookbook thing. But we won't do too much of that. Cool. Questions on this?
If there are multiple points in the range where, well, not quite range, well, range of the derivative. Anyways, if there are multiple points where the slope is 0, does that, like, more than 2? Are they both called maximums or minimums?
It depends. So let's actually, yeah, let's do something that looks like this. I've drawn a fucky sine function, right? It's like a sine, but it oscillates a little bit. So this one's higher than that one or something. So here's an example of what you just said, because you said suppose there's more than 2. So here there's a bunch. There's 1, 2, 3, 4, 5, 6 points on this range, this interval, I should say, where the derivative vanishes. So all of these happen to be local maxima or minima. Remember, our definition of local max and min is that you can find some delta so that on a tiny delta interval around your point, he's actually a maximum point in the way that we defined it. He's the biggest guy on this restricted interval. So in this case, all of them have that local max or min property. But of course, there can only be one global maximum value, although there could be multiple global maximum points. So the global max for this example occurs here at the blue point, and the global min, the way that I've drawn it, occurs down here at the green point. So good, yeah. So to answer your question, yeah, you can have more than 2 with that property, but in many examples, only one of them will be the true maximum. As one other counterexample, what about the ordinary sine function, the real, not distorted sine function? In this case, you can have multiple global maximum points, right? Because the values are equal at all of these. So this is different from the above example because all 3 of these points are both local maxima, because I can make a tiny interval and he's bigger than everybody on the tiny interval, but they are also all global maximum points because their values are all equal. So you have to be careful. All of the cases are possible. It could be that, Could be that there's only one. It could be that if I made this guy a little taller, there could have been two global maxima. They could all be global maxima. You actually have to compute all the values and check is the punchline. Good.
So could you compute whether something is a global maximum just given the derivative?
No, you wouldn't know unless you actually had a list of all of the points in these three classes, and you knew the value of the function at those points, not its derivative. Knowing the first derivative isn't enough to tell you whether it's a global max. You need to also know the value of the function. So you just basically compute all these points and then put them in a list from smallest to greatest. And then you know the greatest one is your global max. So yeah, so you need more than the derivative is the answer.
Okay, so it's simply, how do I word it? Finding the maximum is still a human activity, even if it's made easier by the fact that we know that the derivative is going to be 0 now.
Yeah, human in the sense that, I mean, for you to do it requires work. You have to actually look at them and decide. Hopefully it's fairly clear that the process the human does when he looks at those points and takes the biggest is of course something that a computer could do as well. So, I mean, in Mathematica, you can just maximize a function on an interval, and it will go through this process and pick the largest one for you. Or even if you don't have a nice formula for the function, if you only know, an approximate numerical way of computing, the values of the function at certain points. So maybe you don't have a formula for it, but you know that if I evaluate it here, I get this, and you just have a couple scatter points, and you don't know how to connect them to form a smooth curve, but you know roughly where the function is. There are so-called optimization routines that try to sort of approximate this algorithm in some sense, even though you don't have all the information. There are optimization routines that'll try to find the max and min. I mean, they're very standard. They're written in Python, like NumPy and SciPy have them. So to answer your question, is the process which I've just outlined here still something which requires a human to look at it? No, not necessarily. That's just what we'll do in this group. And if you take a calculus test, of course, it will require you to look at it because you don't have a computer. But it is something which can be automated, and there's a huge industry of people trying to find better, more accurate, more numerically stable optimization routines. I mean, I spent a lot of time using these when I was working at CERN and working in finance and working with the program for evolutionary dynamics at Harvard. So in all sorts of science, generalizations of this procedure to find the optima for messy functions are incredibly important. Okay, sorry, I accidentally talked too much again, but does that answer, is that close to what you were asking?
Yeah.
Okay, good. Other thoughts? These are good thoughts.
I have no further thoughts.
Excellent. I enjoy your insights. Okay. So the second thing I want to review is this mean value theorem. And this is important because we're going to use it in the proof of this increasing versus decreasing business. So again, the point of this guy was that under the same assumptions as on the previous slide, if f is continuous on the closed interval ab and differentiable on the open interval ab, then the theorem tells you that there exists a number x. So it's important. I mean, a lot of high school calculus students, when they see the mean value theorem, they just forget all of the hypotheses and just memorize this formula and try to blindly apply it. But that kind of defeats the purpose. I mean, you should understand that the purpose of this formula is guaranteeing the existence of some number x. You don't know what x is. The theorem doesn't tell you what it is. It's existence, but it's non-constructive. It doesn't tell you how to find x. So all you know when you use this guy in a proof is that there exists some number x in the open interval ab with the property that at that value of x, the slope of the tangent line is equal to the slope of the secant line between these two endpoints, right? So in the place I've drawn at that point, x is this thing c, right? So just tells you that there's one. And one amusing application of this is I think EasyPass and some other automatic toll services like iPass in Illinois have started implementing a sort of automated ticketing scheme. The way that it works is if you have, you have Easy Pass 1, if there's a station here on the road, and then you have a second Easy Pass, so this is Easy Pass 1, and you have a second Easy Pass station here, which is Easy Pass Station 2, and if the distance between those two is d, what they do is they get data on all of the cars driving on this road about when their Easy Pass tag fires because they went through the Easy Pass, and they have very precise time. So they know exactly at what time you passed this point with the first Easy Pass, and they know exactly at what time you passed the second one. So what they do is they take the distance and divide it by the time that it takes you from going from the first one to the second one. And if they compute that number and it's greater than 65 miles per hour, which is on most of the Pennsylvania highways, then you might say, well, okay, so maybe this is like 100 miles. So if this thing is like 100 miles and I get there in, 20 minutes between them, yeah, I was going pretty fast, but how do you know I was speeding? Right? You weren't there like a cop sitting by the side of the road with a radar gun. You never saw me speeding, so how could you possibly know that I broke the law if I went 100 miles in 20 minutes? Well, what they would say is, yeah, well, we never saw you speeding, but we know that you went 100 miles in 20. That's too much. Sorry. Maybe.
That man deserves an award.
Man. Yes, I picked a bad one. I wanted larger than this, so 100 miles in, I don't know. Let's see. I want something that's close. Why don't I should pick better numbers. So, 100 miles, well, let's make it very easy. 100 miles in 1 hour. That guy was going very fast. Okay, so you go 100 miles in 1 hour, so your average velocity between these two Easy Pass points was 100 miles per hour. So you could, again, make the argument, how did you know I was speeding? Well, we know that the slope of the secant line, the average velocity between those 2 points, was 100 miles per hour. So by the mean value theorem, we're guaranteed that somewhere you were speeding, right? There has to be at least one point along this path where your instantaneous speed was 100 miles per hour, which is greater than the speed limit. So they send you a ticket and say, we knew you were speeding. So it's kind of fun. Even though there's no cop who actually saw it happen, you can guarantee it's true. Okay, thoughts on this?
I have no thoughts.
Good. Now we can get rid of all cops if we just make everyone have Easy Pass. Alright, so here's a challenge for you then. So you'll remember last time we used the mean value theorem on the previous slide to do this proof, right? The proof was that if the derivative is 0 at every single point on an interval, we prove that f is constant on that interval, right? Remember this, the idea of the proof was that we used the mean value theorem to say there's always some x where the derivative of x is going to be equal to the secant line slope between 2 points, which I think we called c and d there. But even though we only know that there exists one point x where this is true, if we're guaranteed that the derivative is 0 everywhere and b is not equal to a, then we concluded f of b is f of a. That was the punchline of the proof from last time. Okay, so can you use this result? We don't have to repeat the proof. If you're clever, you can just use this result with a slight modification to prove this new thing. Here's the thing we want to prove now. Two functions f and g are now defined on the same interval, and their derivatives agree at every point. So f prime of x equals g prime of x at every point x in the interval. Assuming that's true, we would like to prove that there exists a number c, the constant. There exists a constant c, such that f equals g plus c. So in other words, the two functions f and g, if their derivatives agree everywhere, one of them just has to be a horizontal translation of the other. So if this is f and this is g, it's horizontal, sorry, vertical translation. Can't talk. There's some number c, so that f equals g plus c. They're just the same function offset vertically by some number c. That's what we want to prove. Okay, so what do you think? Well, think about it for a minute, and then if you have an idea, how can we use the result from last time to prove that?
Could we somehow say that f is the secant line? Oh, wait. That's what we are trying to prove. Never mind.
This thing, that f and g are related by a constant is what we're trying to prove? Is that what you were going to say?
It would seem that by letting f be the secant line of g, we are making both an additional... Well, we need to somehow prove that secant line has that property.
So f won't be... This property doesn't mean that f is the secant line of g necessarily. This means that f and g are the same function more or less, but offset vertically, right? So that's different from being a secant line.
Right, I don't... That makes... Now that I think of it, that makes 0 sense.
That's okay. It's good to generate ideas. You have to say all of the things that come to mind and then slowly filter and winnow out the good ones. All right, let's use one of my favorite strategies is when you're stuck, write down what you know. And
okay.
What is it? Do you have an idea?
Well, there's a lot of noise going on, but I was going to say we could write down the definitions of derivative for each of f and g.
We could, yeah. We could use the difference quotient definition to get f prime and g prime. But I think there's a faster way that only uses the result from last time, so we won't have to appeal to the difference quotient necessarily. Let's just write down the pieces we know and see how to fit them together. So we know if a function... I don't want to use f twice. So from last time, we know if a function always has zero derivative, then h is constant, which means h of x equals some number c. That's what we know from last time. And we also know that these two functions, f and g, have the property that f prime of x equals g prime of x everywhere. And so this is what we know. What we want is that f of x equals g of x plus c. So do you see a way to combine the two bullet points that we know, the assumptions, in order to prove the bullet point that we want?
Stop. Making sure I'm paying attention.
No, I mean, maybe that was a bad thing, so now I'm distracting you. But can we cook up a function h so that the first bullet point is true? Can we cook up a function h such that h prime equals 0 everywhere?
Let h of x equal c. That is a terrible idea.
Ah, good. Yeah, so that would tell us that constant functions are constant functions. We get a tautology. Good. All right, good try though. What else? What can we build out of the functions that were given f and g that would satisfy the first bullet point? I claim that if we know this thing, if we know that f prime equals g prime everywhere, there is a natural function h that you can build using this equation such that the derivative of h equals 0 everywhere. What function can we build out of f and g which would have zero derivative everywhere?
Are you asking for a constant function?
Well, no, I mean, it should be built out of f and g. We don't know f and g are constants.
Okay.
So define.
Oh, okay. So you could let x equal g of x minus f, excuse me, g prime of x minus f prime of x.
Let's see. So you say g prime of x minus f prime of x. So that, I agree, is 0 everywhere. But we don't want to let h be this thing, because if we define h to be this, then certainly h equals 0 everywhere, but we would like the derivative h prime to be 0 everywhere. So I think, well, it's certainly true for this as well, but I think a more useful definition would be h is just g minus f, not g prime minus f prime, right? The reason for this is that if we define, let's see, so as you told me, this means, I guess you put g prime first. So you said this means g prime minus f prime equals 0. So that means the function, by linearity, g minus f whole function prime equals 0, right? And now we just match that onto our definition here. So we're looking for a function whose derivative is 0 everywhere, and the function g minus f has that property, that g minus f derivative is 0 everywhere, right? Do you agree with this manipulation?
Yes.
Okay. All right, so then it's a pretty direct application of the above theorem, because then since this function has 0 derivative everywhere, we know it must be a constant. So g minus f is some constant c, which means, well, it's the opposite of the constant the way that we want it there, but this means that f is g minus c. So, I mean, just change the definition of c to match this one. Good. Okay. This is a pretty short proof once you see the trick, but it's this very common trick in math, is that it's easier, rather than when you're given something about two things being equal, it's almost always better to subtract one off and then have a combination of two things which equals 0, right? Because all of our things usually are related to certain things being 0. But anyway, okay, that's the review challenge. Thoughts on this?
Can my mic actually go on?
Your mic cut out? What?
I have no thoughts.
Ah, okay. All right, let's do, well, here's the solution again. I did it the other way. Let h is f minus g, h prime is 0 everywhere, because you can just differentiate each by linearity. That means h is constant, and then f is g plus c. Good. Okay, let's do this increasing, decreasing thing that I promised a while back. But first I want to be very explicit about what I mean by increasing and decreasing. So there's the non-strict versions. We actually haven't defined these before. We defined strictly increasing and strictly decreasing in chapter 1. So this is a repeat of things that we've seen before. The only difference is that these first two definitions of the words increasing and decreasing without the modifier strictly is that you allow equality. So a function is just increasing on an interval if f of a is less than or equal to f of b, whenever a and b are two numbers in the interval with a less than b. So for instance, you could have a function which is increasing but looks like this. Maybe it's going up like this, and then it plateaus and it's constant for a while, and then it's back up again. So this function counts as increasing because you can have 2 points a and b where f of a equals f of b, even though a is less than b. but it would not be strictly increasing, because strictly increasing has the less than without less than equal to. Similarly, the word decreasing, function is decreasing if f of a is greater than or equal to f of b whenever a is less than b. So again, this could be like this, where it plateaus and then goes back down. So it can be equal, but has to always be equal to or decreasing. And the strictly increasing, strictly decreasing do not allow equality. So strictly increasing and strictly decreasing functions, as we saw in chapter 1, these will have inverses because they will necessarily pass the horizontal line test. You have to pass the horizontal line test if you're strictly increasing or strictly decreasing, because you can't hit the same value twice at two different points, because this less than guarantees that the two numbers have to be different. So I'll phrase all of the proofs that we do. Actually, I think there's only one, really, in terms of this strictly increasing. But it's pretty straightforward to modify the proofs to see when a function would just be increasing, for instance. But anyway, good. It's good to know what these words mean. So, thoughts on this?
I have no thoughts on this.
Okay, good. Yeah, there's not much to say about it. It's pretty straightforward. But okay, so here's the proof. It would have been hard to prove this without the mean value theorem, but with the mean value theorem, it's very, very fast, which is another reason why the MVT is overpowered. MVT is MVP, if you will. So, okay, here's what we want to prove. Actually, well, maybe it's better if you read this one, because I've been talking a lot.
All right. Actually, is it that great of idea? Are you hissing behind me?
I actually don't hear the background noise you're talking about.
Okay, because it's pretty loud. Anyways, I shall go on. Proposition. If f prime of x is greater than 0 for all x in an interval, then f is strictly increasing on the interval. If f of x is less than 0 for all x in the interval, then f is strictly decreasing on the interval.
I'm glad that you caught my typos. Good. Go on.
Proof. We show the case f prime is greater than 0. The other case is similar. Let a and b be 2 points in the interval with a is less than b. By the mean value theorem, there is some x in the interval where f prime of x equals f of b minus f of a over b minus a. By assumption, f prime of x is greater than 0 for all x in the open interval ab. So, f of b minus f of a all over b minus a is greater than 0. We multiply by b minus a and conclude that f of b is greater than f of a.
Good, very nice. So, worth noting is that we never needed to know what the point x was, right? The mean value theorem, again, only told us there's some place where this equation is true, but we didn't need to know where it's true because we assume the derivative is positive everywhere. So as long as the derivative is positive everywhere, the left side of this equation, circled in pink, will be positive. So you can multiply through by a positive number and get that this thing is greater than 0. Yeah, so as you figured out and corrected me very quickly, I should have said strictly increasing here, because the answer we got at the end was greater than and not greater than equal to. But it's very straightforward to modify the proof to know when a function is just increasing. If you just want the function to be increasing but not strictly increasing, then you can weaken the assumption. You can say if this is greater than or equal to 0, and if typo, f prime of x is less than or equal to 0, then f is increasing or decreasing, but not strictly, because the proof goes through almost unchanged, except this has a greater than equal to. So, great, yeah, it's not magic, but punchline is when the derivative is positive, and only positive, it's strictly increasing. If the derivative is non-negative, then you're just increasing. Good, more thoughts on this?
I have no thoughts on this.
Okay, let's analyze the graph of a function then. So here's a cubic, a function x cubed minus 3x squared plus 1, and we want to find where is f increasing and where is it decreasing. Okay, so what should we do first?
I assume the lazy way out would be to graph it.
Yeah, but I mean, a graph is not a proof. If you graph it and it looks like
Right.
it's increasing, that's not so great. So let's prove it. So what do I need to do to find where f is increasing or decreasing?
I guess. Let me think. Would factoring help us? I don't even know if this can be factored. Never mind.
Yeah, I think that'd be hard. So, um, well, I mean, we have a nice theorem for this, right? So we just proved that you can find where it's increasing or decreasing by looking at whether the derivative is positive or negative, right? So
All right.
what should we do here then?
So we take the derivative of the entire thing.
Good. Okay.
We
So
apply the power rule to each, and constants become 0. To see that this is going to be 3x squared minus 6x plus 0.
good. Okay.
So I had to add the 0, because if I said plus nothing, then it would sound dumb.
Okay. Good. So how do we find where this function is positive or negative? Because we want to know where the derivative is positive or negative.
I'll start by factoring out an x.
Yeah, I'll just go ahead and do a 3x for you. So how about this?
That makes much more sense.
Good. Okay. So where is this guy positive and where is he negative? Well,
It would seem that for x greater than 2, it is positive, and for x less than 2, it is negative.
good. So x greater than 2 is positive. Well, we should be careful. If x is between 0 and 2, then this factor is negative, and this factor is positive, and a negative times a positive is a negative. But if x is less than 0, then this factor is negative, and this factor is also negative, right? So negative times negative is back to positive.
I see.
Yeah, you can see that very quickly by, as you say, graphing it, because the reason we factored it is because now we know where the roots are. They're at 0 and at 2, and this is an upward opening parabola, so we know that if those are the roots, it has to be negative in between them, right? Good, okay, so indeed that tells us where the original function is increasing and decreasing. So we're going to claim the original function f, not the derivative, but this cubic, is increasing when x is greater than 2 and when x is less than 0, and it's decreasing in between on this interval between 0 and 2. So let's actually take a look and see whether that's true. As you told me, the derivative is 3x squared minus 6x, which factors like this. It's positive here, negative there, positive here again. And as you suggested, we could kind of compare our analytical intuition to graphical intuition by just plotting the original function. So this is the original function, not the derivative. And indeed, when x is less than 0, so here's 0, when x is less than 0, so we're on this side, indeed this is positive, the derivative is positive, so this is increasing, and it is. In the regime between 0 and 2, which is right here, you can see kind of graphically that the sky is decreasing. And when x goes to the right of 2, this is increasing everywhere. So our answer analysis checks out. Looks good. Okay, good. Thoughts on this?
I don't know why the concept of a cubic's derivative being a parabola, like, I don't know why I find that funny and amusing.
Yeah, I mean, I guess it's kind of it's fun the first couple times you see it because parabolas feel very banal and mundane, like you've seen them a million times. But cubics, I mean, one rarely like solves cubics unless they're very special by factoring or something. So the fact that a cubic kind of gets, knocked down or cut down to size by when you differentiate it and it becomes a parabola, I think that's kind of cute. Good. Other thoughts?
I have no further thoughts. Stuff is getting louder. There's a lot of water for whatever reason.
Fucking sump pump. Okay, let's do PVA then. This topic is often abbreviated in high school calc classes as PVA, but I could never do that. I think I use it later jokingly, but every time I read the acronym PVA, my brain just thinks that must mean penis, vagina, asshole, and I don't
I am
know.
tempted to Google this.
I don't think that's an actual thing anyone has ever said. I just have Tourette syndrome or something. I don't know.
Wait, no, that's not what I was talking about. I was thinking about if PBA is like super common.
Super common is an abbreviation for this, you mean?
Yeah.
Yeah, I think only in like AP calculus. No serious college calculus courses call it that, I think. But I'll just use
Good.
it. Okay, so quick thinking back to when we started derivatives. So we spoke about Newton's motivation when studying, say, a falling apple or something, and trying to understand what is its speed at any point. And for an object which is moving kind of in uniform motion, it's just kind of rolling to the right with a constant speed. It's very easy to define what you mean by that constant speed. You just measure the slope of the line. But the issue with a particle whose speed is changing is that it's not clear what you mean by the slope of the line at a point to a curve, because a curve does not have a slope. But as we saw in kind of the last chapter, there's a way to circumvent this problem, which is Newton's idea of finding this instantaneous velocity by taking the average velocity between two nearby points, where nearby now means separated by a short distance in time. Say maybe you iteratively reduce the time. I don't know. Here the difference between this t1 and t2 is 0.6 seconds, then you can reduce it to 0.1 and so forth, make it smaller and smaller in a limit, and then find the slope of these 2 points separated by that small delta t. And the idea was that in the limit, as delta t goes to 0, this thing defines a derivative. So our first and kind of perhaps most important model for what the derivative is as the instantaneous velocity of some particle. That was the idea. Okay, so that was the picture, but when we did this last time, it was just hand waving. There was no rigor behind it. But now we can come back with the full rigor of calculus, because now, down to the groundwork, everything in these sentences has been rigorously defined. Every derivative has been rigorously defined down to epsilons and deltas, and we've proven everything from scratch. So now we can make that intuitive notion precise. So we're going to make some definitions. I love when math books do this, because it looks like you forgot the end of the sentence, but the sentence actually finishes here. So we can make some definitions. If x of t is the function which represents the position of a particle, and to be very precise, what I mean by position is that you set up some origin of your coordinate system, and then the position is the distance in meters or some other unit you like, the distance between the particle and the origin of your coordinate system at a given time. That's x of t. The definition of the velocity, v of t, is the time derivative of x of t, dx dt. And in particular, when we use derivatives with respect to time, it's very common to use this dot notation, an over dot, instead of a prime. Now I should make a correction, because I, in my head, just call these two things prime notation and dot notation. There are actually people's names that go along with them, and I've been saying them wrong. This whole time I've been saying, when we spoke about prime notation, I've been saying that f prime is Newton notation, but that's wrong. The prime notation is associated with Lagrange. So this f prime is really Lagrange notation, and it's the dot, the time derivative that I've introduced here, the over dot, that is Newton notation. So again, the dx dt is still Leibniz notation, I got that right. The prime is Lagrange notation, the dot is Newton notation. Good. Okay, so that's the definition of velocity, and as we alluded to before when we were talking about the particle in gravitational fields, acceleration is now the second derivative of position, which is the first derivative of velocity. So dv dt is the same as d squared x dt squared, or x double dot. And in LaTeX, this is slash d dot x double dot. Okay. Um, yeah, no math here, just words, but questions on the words.
Is this the same Lagrange that Lagrange points were named after?
Yes, this is Joseph Louis Lagrange. He also his several concepts bear his name. Lagrange points in orbital mechanics, the Lagrangian in theoretical physics, Lagrange multipliers in optimization. He did a lot of stuff. But yeah, same guy.
And he discovered all of these. That's awesome.
Yeah, this was back in the day when there was a lot of discoveries to be made, and one person could be kind of a polymath, good at everything. Good. Other thoughts?
I have no further thoughts.
Okay. All right, let's do another example. So you'll see that, problems about position, velocity, and acceleration are almost identical to problems about analyzing graphs. We're just kind of putting different flavor text. We're just draping different words around the same calculation. So here I've just written down another cubic, but now it's a cubic in the variable t, so a function of time. And we're now going to think of this as not just some random cubic the way that we did a few slides ago, but we're going to interpret this physically. So we say that this thing is now the position of some particle as a function of time. So I'll ask you, what are the velocity and the acceleration of this particle? And then using those, we'll try to describe the motion just qualitatively, talking about which way it's moving. Okay, so first, what's the velocity v of t?
So I'm weakly trying to remember. I believe that this is just, I'm hoping that it's not just recalling, but I'm going to just recall. Is it going to be the derivative of what we see here?
Yeah, so velocity is the derivative of x with respect to time, right?
Okay, cool. So we're going to have 6t squared minus 42t plus 60
Good.
plus.
Plus
I
0.
keep saying plus. Why?
Good. And now you see why these numbers have been cooked up, because if I pull out a 6, that 42 gives us a 7, plus 10, and this guy factors nicely because product 10 and sum not minus 7 looks like minus 5 and minus 2 work. So we can factor this as t minus 5, t minus 2. But anyway, that'll be for later. Don't use this to take the next derivative. You can still just use this thing on the far left, but we're going to use this later to interpret it. But anyway, okay.
Right.
So acceleration.
The acceleration is going to be thinking 12t minus 42 plus 0. I keep saying plus 0. It's a bad habit.
It's fine. You can say plus 0 as many times as you want. Multiple times in one equation if you want. Okay, so now we can do some interpretation. So we see that the velocity, which is instantaneously the direction that the particle is moving, changes sign at t equals 2 and t equals 5. So say at time 0, which is before both of these, at time 0, if I plug in 0, these guys go away and I'm left with 60. Right, so the initial velocity is that the particle is at t equals 0, the particle is moving to the right, because positive in our conventions, remember positive is always the distance from the origin, so since the right is positive on a number line, it's also positive here for our particle in some units, maybe 60 meters per second if you like. Then at t equals 2, this product is now negative, so for t between 0 and 5, this guy has changed directions. He's now moving left with, some varying speed. And once we get to t equals 5 and beyond, he again changes directions, and now both of these are positive, so for t greater than 5, he's back to moving to the right. Good. So this thing jumps around a little bit, and by looking at the acceleration, we could see that initially the acceleration is negative, which means this guy is decelerating. So at time 0, he's moving to the right, but he's slowing down because his acceleration is negative. And now we see that makes sense from the interpretation of this change in direction, because since he was slowing down while he was moving to the right, he eventually slowed down and stopped, and then began moving to the left. And then the acceleration we see changes sign. So this is kind of like a turning point or inflection point, if you will. So a equals 0 at what's 42 over 12 is 7/5, is that right? T equals 7/5.
Yeah. 21 over 6?
Wait, I went 42 over 12, which is 21 over 6, which is 7 over 2, right? Because I'm dividing by 3. Good. Yeah, sorry, not 7/5. 7/2, I think. Good. So here is when the acceleration changes sign. So the acceleration goes from negative to positive here, right? Because beyond this, at large times, the acceleration is again positive. So he's back to moving to the right, and he's moving to the right faster and faster when we get to large time. Okay, so we've dug in rather a bit. It's good to kind of check this and then do some answer analysis. So again, I'm going to mix up every time we introduce new notation. I'm going to use all 3 of them. So I'll now use Newton notation in addition to Leibniz and Lagrange. So this is the velocity we found. Here's the acceleration. At time 0, the guy's moving to the right, as we said, but slowing down. Then the particle changes direction. He moves to the left for a while, and then moves to the right eventually. And I think I did this wrong. This is why I said 5/7, because I made a mistake when I was writing the slides. As you say, this should be 21 over 12, which dividing, 42 over 12, and dividing top and bottom by 6 should be 7/2. So t equals 7/2 is the correct time. The acceleration vanishes. A equals 0. So that's where the particle changes from accelerating to the left to accelerating to the right. Good. Let's look at a picture to analyze this. So this is x as a function of time. So let's see. We said between 2 and 5, the particle is moving to the left, right? So you have to interpret this graph correctly. I mean, again, this is the distance from the origin in some coordinate system. So at time t equals 2, on the right now I'm drawing an actual snapshot of where the particle is, not the position graph. This is just literally where the particle is. At t equals 2, the particle is 60 meters away from the origin. And then later at, say, t equals 5, now the particle is down to something like 30 meters, it looks like, from the origin. So that's why we say that the particle is moving to the left, because this vertical axis is measuring his horizontal distance from the origin. So when the height of this curve becomes lower, that means the particle is further to the left. So indeed, he was moving left here, and he switches to moving to the right, eventually faster and faster. At large time, should really be t. And back here, he's again moving to the right because his x-coordinate, which is graphed vertically, is increasing. Okay, good. So it's just good not to be confused about the difference between position versus time graph and the actual physical position at a given snapshot, right? So, even though this is the vertical axis, higher means further to the right. Good. Okay, thoughts on this?
You have now got me hyped about physics.
Well, this is just kinematics. I mean, this is the widely regarded as the most boring part of physics, but it's a start.
It seems really cool.
Good. Yeah, I guess you probably haven't done any since you didn't have 9 general science, so you probably, I mean, not that that counts as science, but nice. Other thoughts on particles moving?
I have no further thoughts.
Okay, so let's just to solidify our intuition about PVA, I'm going to stack 3 graphs, position, velocity, and acceleration, all together. And let's zoom in and just think about this a little bit to make sure we can interpret all 3 of these. So this is now, again, position versus time. So again, higher here means further to the right. So let's see how the relationship between these 3 graphs work. So first, let's just focus on x, right? X is in meters, so this is the top one. Time is increasing on the right, on the horizontal axis. So the particle starts right at the origin, right? X equals 0 means he's sitting right on the origin. We wait for a while. This increases, which means the particle is moving to the right. And the slope of this line, which is his speed, is getting steeper. So, well, here, the slope is getting steeper at least. So he's moving to the right, and he's doing so faster. Then in this regime, between the dotted lines, as the speech bubble says, here the slope is constant, so he's still moving to the right, but he's moving to the right with constant speed. Then in this regime, up here in this big hump, he's still, at least for this part, moving to the right because his distance is increasing, but he's slowing down because the slope is getting smaller and smaller until we get to this important point at 15 seconds. So here, I mean, right here, he's just kind of sitting right at some fixed distance, but he stops for a moment. He's not moving at this moment. Then he starts to change direction. Here, the height is getting lower, which means he's getting closer to the origin, which means he's moving to the left. So here he's moving to the left. Then back down here eventually, the slope, which is his speed, is decreasing again, so he's moving to the left but slowing down. And then finally he stops. And we're supposed to imagine this as just being constant forever. So he starts at the origin, goes away, stops, comes back, and doesn't quite make it all the way to the origin. Then he just sits at some constant distance, say 40 meters from the origin, forever. That's position. How do we interpret that in terms of velocity? Well, velocity starts out being positive and increasing because he's speeding up in this regime. So the velocity is positive and it's moving upwards. Here, when he has constant velocity, where the slope of this line is a constant, we see the velocity levels off. Then here, when he's slowing down means the velocity is decreasing, so the velocity is getting smaller and smaller and smaller. Notice this relationship between the point where he's not moving, which is a critical point. That means where the derivative is 0. So the point where he's not moving, the derivative is 0, and indeed the velocity goes through 0 at that point. Then here, he's moving back to the left, so we see our velocity getting negative, and it's getting larger, so he speeds up to the left. But then finally, he slows down, and he's going to eventually get to 0 velocity, because he sits at rest forever. So we see the velocity coming back up, and then it hits 0. That's the second interpretation. The third is in terms of acceleration. This guy is very jumpy, the way that it's drawn, so the acceleration is discontinuous. The acceleration is positive here when he's speeding up. It's 0 here, where he's moving with constant velocity. Here it's negative because the particle, first he's slowing down but moving to the right, and then he's speeding up and moving to the left, so that's a constant negative acceleration. And in this regime, although he's moving to the left, he's slowing down. So if you're decelerating, well, you're moving to the left at a slower rate. That's the same as accelerating to the right, right? Decelerating towards the left is accelerating towards the right. And then finally, when he comes to rest, the acceleration indeed must also vanish since he's not moving. Okay, so I mean now you see why the first and second derivatives tell you a lot about a function, because we can kind of read off important properties of this guy's motion just by stacking these 3 graphs, and they line up very nicely. Good. Thoughts on this analysis?
have no thought about this.
Okay. All right. Well, uh, I will put words in your mouth and say a thought that you could have had. So upon
It's going to be concavity.
no, it's not. It's going to I think a very natural question to ask. One could say when seeing this is, well, why wouldn't you keep going? What's so special about the second derivative? Why did we stop at acceleration? I mean, in this case, when we take the third derivative, it's just going to be zero, or not defined at some places. It's not defined at these discontinuities of acceleration, but you could say, for general motion, why wouldn't you take more derivatives? And the answer is you can, but from a physical perspective, they're not very important. And this is the reason. Well, first, their names. Their names are a little silly. I think we've discussed the jerk before. So the third derivative, triple dot, is called the jerk. The fourth derivative with 4 dots over it is called the jounce. I think these are actually a joke. People actually made these names, and sometimes people use the words, but I think this is just a reference to a certain breakfast cereal. They call it snap, crackle, and pop for the fifth derivative, sixth derivative, and seventh derivative, and so on. But although engineers occasionally measure these, they never appear. I mean, I can probably count on one hand the number of times I've seen third derivatives appear in serious physics contexts, and all of them are in approximate kind of theories, not... What do you say?
Jerk, like sudden changes in acceleration. I mean, the name makes sense. So that could be seen in engineering quite a bit.
Yeah, so it's certainly something which happens, right? It's seen in engineering, and maybe you want to measure it if one of your materials has some fault tolerance, like you know that it's going to break not when the acceleration exceeds a certain amount, like a human breaks when it experiences too many g-forces. That's acceleration. So if you're designing a space shuttle, you want to know the maximum acceleration because that's something that the astronauts are going to feel, and it will kill them if they experience too many g's. I agree in certain mechanical engineering applications, if you're working with materials, it might be that a steel beam can handle high accelerations, but it can't handle big jerks. That could happen, and it does happen. Um, so jerk and jounce are things which exist and can be measured, and non-trivial motion is going to have non-zero values for these functions. But from not an engineering perspective, but a physics perspective, physics means just trying to write down the laws of nature that tell you how things behave. Uh, and if you're trying to do that, you actually never need jerk for fundamental theories, at least. And the reason is quite profound. It's really that we've in every field of physics, from classical mechanics to electromagnetism to general relativity, even the laws of quantum mechanics, it seems that all the laws of nature, all of the fundamental equations that describe deep down how the smallest pieces behave, they all tend to be at most second order in time derivatives. By order, I mean the number of derivatives you take. So second order means nothing beyond acceleration appears in fundamental equations. I should say fundamental. Of course, there's approximations where you say, okay, well, the fundamental equations are hard to solve, so I'm going to use some approximation. Maybe that has the jerk. But I can count on one hand the number of times I've used that in a serious context. So the classic example of a fundamental equation, which is second order in time derivatives, is Newton's second law. So, I forgot the proportionality constant. This is F equals ma, right? I've just written it with some extra decorations. I've written F as a function of the position of the particle. By this I just mean that if the particle is moving in some force field, then the force which it feels is a function of where it's sitting. So if you change x, you move where the particle's sitting, he's going to feel a different force. Maybe he's in an electric field, so when you move him around, he feels a stronger electric field and the force is different. So on the left side is the force. On the right side is the second derivative of the particle's position with respect to time times some proportionality constant called the mass, which, I mean, if you're a lazy theorist like me, you usually choose units where I say I'm going to set m equal to 1 so I don't have to write it anymore, and that's why I actually didn't put it on the slide. But, okay, so if you're not a theorist and you like to have masses, then you should write F equals ma. The remarkable thing about this equation, though, is that this is telling you that if you know where a particle is, and you know how certain forces behave like gravity and electromagnetism, you automatically know the second derivative of the particle's position as a function of time. And as we saw before, you can kind of go backwards. If you know the second derivative, you can guess the first derivative up to maybe a constant, which would differentiate to 0, plus 0 as you keep saying. And you can guess the function itself up to maybe 2 constants now. But it's quite remarkable that we never needed to go to a third derivative, right? It stops. The tower of derivatives stops at 2. You know, once you know the 0th derivative, the function itself, Newton tells you that you know the second derivative. You know the function, you know its second derivative. That's it. Uh, there's an interplay, a back and forth between x and a, but not the jerk, not the jounce, nothing else. So this is a very deep result. I've written it down for classical mechanics. The same thing is true in general relativity. So Einstein's equation is r mu nu minus a half g mu nu r is 8 pi t mu nu. It doesn't really matter what these objects are, but all you need to know is g mu nu is kind of like the function. This is like this is analogous to the thing x of t. And these guys, the two things that involve r, are approximately second derivatives. I mean, it's actually, I'm saying approximate, but it's actually precisely true that r mu nu and r only contains second derivatives of g. So it's just like x and 2 derivatives of x. It's true for GR, true for electromagnetism, it's true everywhere. So anyway, that's the answer to the question of why not more derivatives. Thoughts on this?
So why not more is basically we don't know.
Yeah, I guess at a deep level, you can ask, why is it true that nature's laws only involve a second derivative? When you ask that question, you are no longer doing science, and now you're doing philosophy. So I prefer not to answer, or attempt to answer that question.
Avoiding the existential crisis.
Well, yeah, but I'm a scientist, so I only try to answer questions that have, precise meaning. And the question of why did nature choose to only use the second derivative instead of the higher ones? That's not a very precise question. That's just navel gazing.
Alrighty.
Good. Other questions or thoughts?
I have no further questions.
Okay. Well, now, as you say, I will do some concavity stuff, or begin doing it at least. But first I want to do a little intuition. So before we dive in, because the concavity stuff is pretty dense, I want to just do a sketchy argument to convince you that maybe the second derivative should be related to something like concavity, or the direction that a function opens, like whether it opens up or opens down, like a parabola. So this calculation I'm about to do, I should really put like quotation marks around all the equal signs, because this is not rigorous. I could prove this if I wanted to, I'm not going to. So this is really, these are equal up to the fact that I'm being sketchy. But anyway, so if you're willing to brush some things under the rug, I want to play a game with the second derivative to convince you of something. So here's the game. Take the second derivative. The definition of any derivative is the difference quotient. So it's the limit as h goes to 0 of the first derivative, f prime of x, minus f prime of x minus h over h. So you could say, why didn't you use the usual definition that we've used before, which would have been f prime of x plus h minus f prime of x over h? Intuitively, maybe it makes sense that this is going to be the same limit, because if you compare a point a little bit to the right with x itself, and the function's derivative is continuous, then that's going to be the same as comparing the point to one a little bit to the left. But I haven't proven that. I'll prove it on the next slide, but this is the first sketchy thing. For now, you can just take my word for it that this is the same as the usual definition of the derivative. Alright, suppose you believe me on that. In the next line, I'm going to take this h and just move it outside as a 1 over h, so we don't have to worry about it. And now I'm going to plug in the definitions of these derivatives, right? So now I'm taking f prime and putting in its definition in terms of a limit. we're all inside a limit as h goes to 0. So I might as well just replace this f prime by its definition, f of x plus h minus f of x over h. So that's f prime at x plus h, well, f prime at x. In this guy, you have to be a little careful because the thing inside the f prime is x minus h. So the first piece is supposed to be x minus h plus h, which is back to x. And then the second piece is supposed to be the argument itself, which is x minus h. Good, so in this line, supposedly, I've just taken the two first derivatives and put their difference quotients in. Okay, but now we can combine and get one denominator, because these are all over h. So I'm going to combine these into one fraction. Now there's an h squared downstairs from 1h here, 1h here. So h squared in the denominator, and in the numerator I have, well, just all these terms. I have f of x plus h went here. 1 of the minus f of x went here. Now be careful about distributing a minus sign, right? Because when you distribute a minus sign, the minus sign goes onto f, and it also goes onto minus f of x minus h. So that guy changes to a plus f of x minus h. So we got that guy, and then we have a second copy of minus f. So I combine those two like terms, minus 2f. So that's just algebra. Now the last step is to pull out a factor of 2. So I'm going to put a 2 with the h squared, the 2 over h squared overall. And now I just interpret these three terms in the numerator in the following way. I take the first one and the last one and put them together in this fraction, which now has a 2 downstairs, so that it will cancel this 2. And then I take the f of x and just put it over here. That guy doesn't have a 2 anymore because I pulled out the 2 overall. Now there's a very nice interpretation of this thing inside parentheses, because this thing is the difference between the average, this is an average, right? It's the average between f at x plus h and f at x minus h. So this is the average value of f a little bit to the right and a little bit to the left of x. This guy is the value at x itself. So if the function looks, again, I think we've seen this picture a couple times, but if the function opens upwards, and I take the average of the function a little bit to the left and a little bit to the right, so now this is, x minus 8, well, yeah, whatever, I'll just use h, x plus h, and x. The average between those 2 points to the left and right is going to be larger than the value at the middle. So that means the difference inside here will be positive, so the second derivative is positive. That's the idea. Same thing if it's upside down. If it's a cap, then the difference between the average and the function value itself is negative. So this is the sketchy reason why concavity comes from the second derivative, because the second derivative is measuring somehow a local difference between the average value of the function and the function's value itself. Okay, thoughts on this?
I have no thoughts.
Good. Okay, let me just make some caveats about what the sketchiness was. So there's two things I swept under the rug. One of them I'll actually fix now, and the other I won't. So this I flagged for you, this different definition of the derivative, where you put the x minus h here instead of the x plus h here. We can actually prove that's the same as the usual definition, because way back in chapter 2, you wrote out, I think, an epsilon delta proof in one of the daily challenges for the limit of a composite of functions. Right, so if you have a limit as x goes to a of f of g of x, that's the same as taking the limit as x goes to g of a of f of x. So it's replacing the thing inside the limit by a new variable and then sending that variable to the kind of target it would have hit on the left. So we prove that under the assumptions that both f and g are continuous. So in fact, the thing I showed you in the previous slide is true if the derivative exists and is differentiable, and the second derivative exists. So you need at least see 1 and 2 derivatives. Here's the proof. The reason is, if you take the usual definition, here's the usual definition of the derivative. Now I'm going to use this theorem up here with the function g of h is going to be minus h. So I can take the limit as h goes to, well, the image of 0 under this function. If h goes to 0, then minus h goes to minus 0, which is still 0. So I don't have to change the bounds in the limit. I do have to change the piece that goes inside the function. So I have to change all my h's to minus h's if I want to use this theorem. So the f of x plus h goes to an f of x minus h. This piece stays the same. The h downstairs goes to minus h. And now I see that I can just take that minus sign and pop it upstairs. So when I pop it upstairs, the f of x becomes positive, the f of x minus h becomes negative, and the whole thing is still the limit as h goes to 0. So that's the proof that we can use either of these. So that's actually not that sketchy. That's totally fine. The thing which is totally wrong and wrecks this proof, well, I mean, it doesn't wreck it. It's the claim is still correct. The proof I just gave you is not actually a proof. Is that somehow I did this strange skeevy thing where I wrote the first difference quotient with a dummy variable h, and then I said, now I'm going to plug in the definition of the derivative for these guys. But nobody ever said that the dummy variable in those limits was the same as h. These are double limits, right? So this is, I mean, to be totally rigorous, this should have been a limit as k goes to 0 and a limit as l goes to 0 for h, k, and l, all different dummies. And, okay, well, if you take multivariable calculus someday, then you'll handle iterated limits. You can under some reasonable assumptions, you can find some theorems for the way that iterated limits behave. H goes to 0 and k goes to 0 and so forth. But I think it would take us too far afield to actually justify that for now. So I will content myself with making the caveat that the thing I just showed you is not actually a proof, even though the result is actually true. Okay, thoughts on this?
I do not have any thoughts or questions.
Nice. All right, that was the intuition. So now let's dive into concavity. So first I have to tell you what the words mean. I think actually telling you what the words mean is more or less all I'm going to do today. Then we'll do proving stuff next time, perhaps. But anyway, so these words are very confusing. There's the words convex and concave, but people sometimes add extra modifiers to tell you down or up. So it's very confusing. I usually prefer to use a version that explicitly says up or down. So convex down. So convex tells you the way that it points, right? So this thing is convex down because it points down. It looks like a V where the V is going down. So people often just say that as convex. But a function f is convex on an interval if it looks like a V that points down. Confusingly, you can also call that concave up. So concave up means that it opens, the direction the function opens is up. So again, convex down is the same as concave up, because pointing down is opening up. Alright, anyway, here's the definition. So a function f is convex down or concave up if, for all a and b in the interval, the line segment joining 2 points a f of a and b f of b lies above the graph of f. So that's shown in this picture down here. This guy's concave up because if we take a point A and a point B larger than A and draw the line segment between those 2 points, everywhere this line segment is above the graph of f, right? It's vertically higher. So that's concave up. The fairly obvious generalization is that a function f is convex up, so it's like a V which opens up, convex up, which is the same as, of course, concave down, since if you point up, you open down. I can't concave down, damn it. Anyway, so the function is concave down if same thing, except now the line segment is below the graph, right? So fairly obvious. Here's A and here's B. I draw the line segment between them, and that line segment lies below the graph. So, yeah, not rocket science. Draw a line segment and see if it's above or below the graph. I mean, of course, it could be neither. There are functions that are neither concave up nor concave down on an interval. I mean, if there's some places where it's above and some places where it's below, then the function is simply neither concave up nor concave down on that interval. It's maybe has a different concavity on different parts. Okay, so mostly confusing just because of the words, but questions on the words?
You were right when you said they were confusing.
Yes, yeah. I mean, I don't really like it. I mean, if you can just remember the mnemonic that concave is the direction you open, convex is the direction that you point, and if you like, you can just pick one or the other and always say concave up and concave down and never use the word convex. That's fine. Just be aware that when you read different math books, you'll see people alternate between using all of these. Good, okay. Alright, so this will be, I think, the last major thing, and then we can quit and you can do some other work. So, anyway, so the definition we gave is totally rigorous. This is acceptable, but it's a little hard to use in proofs. The statement about the line segment lying above or below the graph, well, we'd like to turn that into something algebraic so that we can actually, write down a formula to prove stuff. So I'm going to convert that to a formula for you. Here's what I do. So we're interested in telling whether the line between 2 points, a comma f of a and b comma f of b, is above or below the graph. So it would be really helpful if we could just write down the equation of that line, right? So the equation of the line between 2 points, a f of a and b f of b. Well, I mean, we've all taken algebra once. We know how to write the equation of a line between 2 points. And here I've done it for you. The straight line between those 2 points, a f of a and b f of b. If you like, this is, point slope form or something, whatever. You can call it whatever you want, but anyway, the slope is, of course, just the secant line slope between those 2 points. So f of b minus f of a over b minus a. So this is the slope times, here we write it in this kind of strange looking way because though the intercept is kind of broken across 2 terms now. But the reason for that, I think, is will become clear. It makes the algebra easier. But anyway, so this is very similar to the observation you made in the proof of the mean value theorem last time, which is the reason why we wrote it in this kind of fucky way, is because now you can see by inspection that if you plug in g of a, well, if you plug in g of a, the first term goes away, and we're left with f of a, which is what we're supposed to get. And if you plug in b, g of b, well, now x is b, so b minus a cancels the denominator. You get f of b minus f of a plus f of a, and the f of a's cancel, and it's back to f of b. So anyway, that's why I'm writing it in the fucky form. But hopefully you're convinced this is actually correct. So that's the straight line. Anyway, so what do we want to do with the straight line? Well, we're supposed to decide whether the straight line is above or below the graph. Alright, what does above mean? Above means greater, so good. So if f is convex, which means convex down, or concave up, the line is above f, which means g is greater than f. G is the line, f is the graph. G is greater than f. So we can turn this into algebra. You just take your expression for g, put it on the left side, this is all g, and on the right we have f. So g is greater than f is the desired formula. The way that it's written here is a bit messy, so you can rearrange by algebra. The rearrangement is subtracting f of a from both sides, and then dividing by x minus a. That's it. So you subtract and then divide by x minus a. Now you get this. This is a nice, very symmetric equation, easier to work with. So just to compare, the point of this discussion was that now we have, instead of this definition, which is that the line segment joining a f of a and b f of b lies above the graph, by algebra we've now proven that we can instead use this new definition. It's entirely equivalent to say that f is convex if this inequality holds for all x in the interval. This is going to be our new definition. New definition. And hope it's clear that a totally analogous argument works if you replace greater than by less than. Replace greater than by less than, that means the line is below the graph, which means you're concave, right? Concave down or convex up. Okay, so I'm just going to rewrite that nicely for you. So we've proven that the function is convex, convex down or concave up, if for all a less than x less than b in the interval, we have the equation or the inequality this way. F of x minus f of a over x minus a is less than f of b minus f of a over b minus a. It's concave, so this again is convex up, so it looks like this. If, again, the same inequality but with the sign reversed, greater than. Okay, so yeah, this one, it's just algebra, but I mean, a lot of words to digest. Impressions on this?
I do not have any thoughts or comments. Though, would you mind giving me like a minute to get upstairs?
Yeah, sure, I'll be here.
Cool.
I always managed to choose the days that my father was running.
And your voice again got like quieter and sadder sounding now that you've gone upstairs.
Because usually I have to speak up when I'm downstairs.
Ah, okay. So the volume drowns out the sadness. Good. Possibly a broader analogy for life. Okay, good. Ready to move on?
Yes.
Alright, last thing is a challenge to use this definition. So I actually use the snipping tool so we can refer back to the definition of convexity. But anyway, so this is going to start giving us an idea that the second derivative should be related to convexity because we know that a parabola which opens up has positive second derivative, right? And it certainly appears to be convex down or concave up using this definition. So it seems like the function which opens up has positive second derivative and is convex, and the function which opens down has negative second derivative and is concave. That's the guess. So we're actually going to prove that with the definition now, for a parabola at least, not for anything more general. So anyway, here's the challenge. So using that definition, that weird inequality between two fractions, we're going to prove that the parabola f of x equals cx squared, where c is a constant, is convex everywhere. So convex is this guy. Convex if c is positive, and concave if c is negative. Okay, so I'll remind you of the definition, and then ask you what we should do to start that proof.
I guess we could start by, let's see. I guess we can start by assuming that c is greater than 0 to prove the former definition.
Okay, good. So we'll start with c greater than 0. Okay. So when c is positive, what do I need to check to prove that this guy is convex?
Need to somehow show that x squared minus a squared over x minus a is less than b squared minus a squared.
Yeah, so you said x squared minus a squared over x minus a So let me just flag this. This is, sometimes I write an equation and then I think that I've proven it already. So this is what we need to prove, right? So this is less than b squared minus a squared over b minus a. So did you already divide out the c that was in front of all of these or something?
I did not.
Okay. Yeah, let's write it in for now because I want to be careful about the sign of c. So for now, since f of x is cx squared, I'm just going to write exactly what you just said, but with the c's. So cx squared minus ca squared is this with x replaced with b. Okay, so do you see a way to do some factoring trickery on the left side?
Could we factor in x minus a out of the top on the
Yeah.
left side?
Yeah, so what's left in the numerator when I factor out x minus a? What's the second piece? When you
Another x minus a?
I think it's x plus a, right?
Okay.
Right, x squared.
Oh yeah, that makes sense because inverse of the FOIL.
Yeah, exactly. Okay, good. So we can use the same trickery because the thing we want to, well, let's not write the thing that we need to prove. Let's just reason forward and then prove it. So, good. Okay, so now we can actually cancel these because in our proof, we assume that these are any 3 points with a less than x less than b, which in particular means that x is not equal to a. So we're safe from division by 0. We can cancel these two factors, x minus a, on both sides, so or on top and bottom. So this is the same as c times x minus a. Okay, good. But if we did the same thing on the right side, the thing that we need to prove that this is less than, you would do the same thing. B squared minus a squared is the quantity b minus a times the quantity b plus a. You would cancel the b minus a's downstairs. And oh, why did I do that? Sorry. You cancel the b minus a's downstairs and be left with b plus a. So this side would be c times b plus a. Okay, so to complete the proof, which is to show that the bottom thing is less than the top thing, how do you argue that c times the quantity x plus a is smaller than c times the quantity b plus a?
You need to show that x is greater than b?
Less than b.
Wow.
Right, we want the bottom one to be less than the top.
Right. So we want to somehow show that b is greater than x? Or
Yeah, good. And actually we already know that because in the definition of convexity, we pick any 3 points in the interval that are in order. A is less than x is less than b. Right? So in fact we're in good shape because we already know that x is less than b by construction. So that means c times the quantity x plus a is going to be less than c times the quantity b plus a. But in this step, it was important that c was positive, right? Because in going from this blue step to this pink step, we had to argue, well, c is some positive number multiplying this thing x plus a. So if I swap x with b, since b is larger, then I'm going to have a positive number times something which has gotten bigger. So that's going to make the result larger. But now hopefully you see that if c were negative, you would have gone through this same argument, and at the end of the day, you would have had the opposite conclusion. Because if c is negative, then you would have made the following argument. You would have said, all right, c times the quantity x plus a has to be bigger than c times the quantity b plus a. Why is that? Well, because if I replace x with b, x is less than b, so the thing in parentheses is getting larger, but c is negative. So, wait, did I just do something dumb? Yeah, no, that's right. So the c is negative, so when I multiply c by the larger quantity, then it's going to get smaller. So in replacing x with b, I am multiplying a negative number by a larger positive number, and therefore the result gets smaller, more negative. So that's why when c is less than 0, replacing it with b makes it smaller. Okay, good. Long-winded, but what do you think? Sound like a convincing argument?
Yeah. And now I'm thinking about what is a negative number.
Ah, good. You're thinking about order relations on the reals, right? Negative numbers have this weird property that they flip these inequalities, right?
I'm just thinking about what it means to be less than 0.
Yeah, I mean, if we had started in Spivak Chapter 1 and done, the foundations of mathematics rigorously, we would have defined precisely what we mean by positive and negative number. So, I mean, in the definition from an order relation, you say, we have some field f, which is a set of numbers. Field f, there is an order, which you call less than, which compares elements of f. Compares elements, I'll abbreviate elements of f. And then you define, say, x is negative if x compared to 0 using your order relation means x is less than 0. And then you can prove using the definition of an order relation and the axioms for an order relation, which we haven't presented yet, but then you would simply prove directly from a very small set of starting assumptions that if, say, you have two negative numbers, their product is going to have the property that it's greater than 0, and so forth. So you can prove this. This is something you do as a math major, and it's good to get this intuition because you just build up the definitions of positive and negative numbers and what less than actually means. Some people think it's kind of a silly exercise because you can ask any 6-year-old, is 2 less than 3, or is 3 less than 2? And they'll give you an answer, but that's just because they've memorized what 2 and 3 mean, and someone told them that 3 is what you get when you hold up 3 fingers, and 2 is what you get when you hold up 2 fingers, and they're supposed to say 3 is bigger than 2. They don't have any rigor, they can't prove it. So anyway, it's a bit of a rant, but I think it's nice to go back and replace all of your intuitive ideas of numbers with serious proofs. Alright, last slide is just that solution again. So, so we have to start with any 3 points, a less than x less than b. We have to compute this weird fraction, which, as you told me, is cx squared minus ca squared over x minus a. We can factor and cancel, and that's c times x plus a. On the other hand, the thing that we need to compare it to by the same manipulation is c times b plus a. So, since another way to do this proof in kind of one step, rather than handling both steps separately, you could just say, alright, we know x is less than b, and then you can add a to both sides. This is just using the rules for an order relation. You're allowed to add both sides to an order relation, and it doesn't change the result. And then, if c is positive, there's an axiom that you're allowed to multiply both sides of an order relation without changing it. And if c is negative, the axiom is that if you multiply by a negative number, it reverses the direction of the order relation. So it goes from a less than to a greater than. So that's how you would do both proofs in one for convex and concave. Good, so we did it. Convex if you're an upward opening parabola, concave if you're a downward opening parabola, as we want. Nice, okay. Thoughts on this challenge or feedback or perspectives on today's meeting?
I have no thoughts or questions.
Okie dokie. I can stiffoo then, so you can go do whatever.